Thank you all for coming. There's 4 tracks and a lot of other things to see, so I'm kind of flattered by the attention. Trying to knock this rather picaresque project into a central narrative, I've had to go for sort of why, and then what, and then where next. In this talk, somewhere as a Trojan horse is shoehorned my opinions on best practice when you come to make a hardware synth, and you'll see those as we go along. But otherwise, why, what, and where seem to be a kind of sensible structure, so that's how I'm going to do this thing. We'll start with why this product came into existence and why I happen to be in charge of finishing it, and then we'll look at the signal flow, go in and look at some of the hardware that makes it work, and then some of the firmware issues I discovered as we took it apart, and some of those aspects, and then where we go next with this thing. So, without further ado, I mean, the reason for the why also is the fact that last time I was speaking here, I was speaking under a massive sign saying, just don't, right? There has to be a central propelling rationale to put another synth into the world, because God knows there are hundreds of them. And so part of my taking time to explain why is because I'm very self-conscious of the fact that I advocate not making hardware unless you really don't have a choice. And I think this sort of needed to be made. Here's Chris Huggett. I worked with him at Novation when I joined the company in 2006, and I left in 2013. But over 20 years, he did pretty much every noise-making thing with a Novation badge on, so starting with a base station in 1994, going right up to the peak and summit, which you can probably still see outside this very room. But he was a kind of synth designer. He was freelance as well. And before that, in the 70s and the 80s, he designed a couple of classic synths under his own brand, so the Wasp and the OSCar were both his creations. So very well regarded as a British synth engineer. And I was working with this other chap who was also at Novation with me and left like I did when he got frustrated a few years after I left, called Paul Whittington, the chap on the right, talking to Jack from Anderton's there about this very synthesizer. And he ended up founding a company called PWM because he wanted to make his own synths and didn't really like the cultural direction that Focusrite Novation was going in for various reasons. And you either do what you love doing, or if it's audio, you don't do it for the money, so you find somewhere else to do it. So I ended up talking to him when I went freelance as well in 2018. We had a chat around my dining room table, and the first thing I helped him with the first PWM project, which is this. Actually mostly designed by a Bristol-based synthesizer company called Future Sound Systems, who make a whole load of modular stuff. And they had this product called the Brunswick, which was this really aggressive speaker destroyer. One oscillator, envelopes, VCFs, just self-contained modular synth, and we turned it into something that was a little bit less intimidating. So we put a keyboard on it, and my job there was to provide the control voltage output, so the keybed scanning, the arpeggiator, MIDI control, all of that stuff. They added an extra oscillator to their thing. We tamed it a bit, got it ready for production, got it through EMC. All of the things that I do is basically the breadth and the glue to an operation like this. So that was quite fun. Getting an analog synth through EMC, by the way, is not trivial. It's a really horrible thing to get right because you've got a big control surface there with lots of nice long high impedance lines going through, and the moment you put a chip somewhere anywhere near that, it just radiates like a bastard. Digital synths, weirdly, are much easier to get through EMC. Anyway, that was an adventure. We made it. It's quite nice. And the second second PWM product, I wasn't supposed to be involved with at all. So this is as far as Chris Huggett got. It's his firmware running on his prototype, and as you can see, it's kind of, you plug it in, the lights go on, and it starts to make noise. So it's fully functional, but what it isn't is finished. There are a few aspects to it that weren't finished, which I'll go into later. One of the first, most apparent things about it is there's nowhere to plug in a keybed. So it was just a kind of rack mount proof of concept. Some other things about it, some of those buttons don't do anything, some of those buttons do the wrong thing. And so it was, what we do have there is a very well executed control surface, right? That is a physical specification. It tells you what it's kind of supposed to do. It's got some Chris Huggett hallmarks on it, so a very left to right signal flow. You select your patch on the left, oscillators make the noise, and then you treat it progressively with filters. There's some envelopes on the right, and then finally there's some effects on the extreme right-hand side. So that's quite a logical layout. No screen, because he likes the immediacy of buttons and knobs and always has. There's pretty much one control per function on the synth, so knobs and buttons are plenty. A lot of those things very Chris Huggett-y, but it's a good statement of intent and something to pick up and work with. So, I mean, what I didn't mention, of course, is that Chris was a victim of COVID, but he didn't actually have COVID. He was being treated for cancer in 2019 when he started this project, and things were going quite well. And then, of course, lockdown happened, and he went for 6 months without medical attention, in which time it metastasized. So he thought he was going to be around for a good few years, and so did we. And very, very quickly, he deteriorated. And so we didn't really get much of a chance to do a handover for this project. But pretty much the very last thing he did before he took to his bed for the final time was to sit at his desk and get all his hardware straight, put the last version of firmware on it, wrap everything up, put all the design files in an archive and send them off to us. So it's a kind of statement of intent, really, that he wanted his legacy continued. And so we took that and we did what we could with it. So the Mantis is a hybrid synth. The best way to make oscillators is digitally, because otherwise you have real problems getting the control voltage stable and creating the frequency you want to create. So nice, tidy digital oscillators. You can shape the sound and control things. Then goes through a DAC. And then all the interesting, slightly nonlinear stuff like drives and filters with resonance on that can scream and VCAs, that tends to be done in the analog domain. So we've got control voltages that operate voltage-controlled amplifiers and topologies that work. There's actually two separate paths in this, and from an analog point of view, they can be wired in series or parallel, so you can either have two stereo paths through the unit with two separate voices, or you can link them together and have a nice steep filter. Normally with a hybrid synth, that's where it ends, but we go through the digital domain for final time to add chorus and reverb, because those are two very nice things to have in a unit. So a hybrid synth, that was his layout. I kind of zoomed into this, but I've already really talked about what it does. There's a couple of things I want to highlight about it, though, a little bit further. One is the mix control, and another kind of very Chris Huggett affectation is that he doesn't have volume controls. Everything is a mix pot. And so the main reason for that, I assume, is because it's a kind of quite a musical thing to do. If you have oscillator one on and you tweak that knob, then another sound comes in, and it's just, if you're tweaking as you play and you're riding the potentiometers, it just seems quite a nice way to be able to control the sound. So everything is a blend. The other thing is we've got this width control here, and that's quite interesting too. So you have the two filters. When you change your width control, the cutoff frequencies for one go down and the other one go up, and you end up with this kind of quite formanty thing. Not that sound, this sound. So you can do these sort of formant things that a lot of other synthesizers can't do, just with one control. And if you ask yourself what the antecedents for these are and where they come from, this is the OSCar, which he designed in 1983. And a couple of details you can see are the oscillator balance controls and a filter separation control. And so he's kind of done what he didn't do at Novation. And at Novation, he kind of very much got into the digital synth arena and stayed there. He's kind of gone back and gone through his back catalogue. And architecturally, this is quite similar to an OSCar. The oscillators were kind of quite waspy, and it seems to be a combination it's a bit of a retrospective for him. That was, I think, really what he was trying to get at. And on the right-hand side, just a screen grab so you can see what's going on. The duophonic section there, because you can have two, you can separate the two filter paths, or you can have them operating together, and reverb and chorus. And he's got 6 types there, and we went for 4 in the end because it was just a question of implementation. Main board, rather straightforward. There's one digital rein there that does all of the number crunching. Also scans the control surface, which I consider bad practice, and we'll come to that in a moment. Got a couple of chips here that do digital or analog conversion. You need 4 outputs, 2 inputs, because we're doing hybrid stuff. We go into the analog domain twice. Analog section here, lots of those larger chips are all quad VCA, so he's got 5 of them on there, 20 VCAs in total, operating filters for each per channel, and a couple of other VCAs at the end there to do envelope generation, mostly in a bit of a mixing thing. So it's not a particularly advanced design from a technical point of view. And another weird Chris Huggett affectation that we didn't go with is he always has these 3-position power switches on his board, so that you can take power either from the USB or the DC jack. And I actually had the conversation with him several times. There are these things called Schottky diodes, Chris. You can mix those power things up and then just not care. But for some reason, he liked having the 3-position switches. We did get rid of it because no one else at Novation ever got it. It just seemed like an anti-feature. So the main processor is the one he chose, which is a Cortex M4. It's great for doing a synth on. Everything is is in one piece of silicon, right? It's a fairly fast chip. It's got an awful lot of SRAM, 256K, which sounds like a lot, but it's like 2 seconds of delay, really, isn't it, these days? But it's quite capable. We turn the floating point unit on because there's some startup code provided by the developer kit manufacturer. And one of the early things it does is just run a floating point operation, and it hard faults if you don't turn it on. But I did a find in files for the word float while I was putting this talk together, and it didn't come up once. Everything's in fixed point. Thing about the ARM is you get a barrel shifter for free in every operation, so you might as well use fixed point. No advantage going floaty. Runs at 168 megahertz, which is ample. Some of the peripherals run at 48. The only problem with it really is the flash is quite slow. We have to put 5 wait states in because it's limited to 30 megahertz. We have to run it a bit slower than that because we'd rather have more core clock. But actually, I tried running things in SRAM and tried running things in flash. Most of the time, because of the prefetch and the cache, things are of equivalent speed. And it's incredibly cost effective. ESP32s are cheaper, but you never like deploying something like that in a product like this because the debugging cycles are just a pain in the ass. These are lovely. You can write code and within 5 seconds it's running on the chip. Here's a bit of Chris's schematic. As you can see, it's a 100-pin chip and it's absolutely fully loaded. He's got some digital flash here. For some reason, 512K isn't enough, and I know why that is. He wanted an EEPROM emulator so he could write arbitrarily and not worry about page erasers and stuff like that. We got rid of that. We just wrote a driver and did things a different way. DAC stuff for the analog digital audio converter. There's another one labeled COD for codec, so 2 sets of audio in digital audio in and out. 12 PWM channels. They are the control voltages for the analog side of things. What else has he got? The whole bloody control surface. Yes, so a lot of I/O, and at the top left-hand corner, he's got these things called OSC. So he was trying to use the on-chip digital analog converters at one point as an experiment to see if he could make those do anything interesting. And those didn't get used, so the conclusion was probably no, they're just not good enough. So fully loaded chip, I consider this a bit of an anti-pattern. I stuck another chip on there just to scan the control surface, and actually looking at how his code worked, every millisecond he was interrupting and actually bit-banging LEDs onto the control surface and bit-banging switches in, and reading all of the potentiometers that were on a big multiplexer. So if every 1 millisecond you're firing an interrupt to go and sit in a loop while you bang 80 bits out manually to a GPIO, it's a fairly inefficient use of your time. You've paid for that chip. It's relatively powerful. You want to spend all that time doing number crunching. So I've done what Fabian would advocate doing in his talk yesterday. I've separated the message thread from the audio thread by putting them on different chips. Now, there's a secondary advantage to this too, right? Apart from the fact that you're not wasting time reading a control surface, which a chip that costs 80p can do. And it's EMC. You can stick this on the control board, and suddenly you go from having this, previous slide, massive, great 30 pins worth of umbilical at the bottom here to just using a comms interface. And so what happens in the end is this chip is largely unconnected. Everything there is either audio or USB or comms of some kind. And you're driving the control surface off a separate chip. I mean, please do this. Do yourself a favor. It's well worth the 80 pence. And because you've just got 2 lines of I2C going to the second board, you can stick capacitors on there and they're not a problem in terms of radiation. And the other 4 pins are 2 for ground and 2 for 3.3 volts. So by doubling the pins up, you halve the impedance of them. There's no problems with EMC at all. Everything just works. Everything is self-contained. So from a design point of view, it just makes sense to do that. And I don't know why he was trying to integrate the control surface into the chip. That comes in play later as well. And also, for the love of God, I haven't seen most of the synthesizers I've taken apart and seen, and none of the ones I've designed, try and do key scanning on the same chip that's running everything else. Keyboard scanning it's incredibly critical. Nobody seems to appreciate how critical, because I don't think musicians design keyboards in the main. But here's a velocity curve that we designed for Mantis. You've got milliseconds on a log scale at the bottom and a velocity on the Y scale. And if you have a look at everything between 7.0 and 7F, the intercontact time between the top key switch activating and the bottom key switch activating, where you're measuring velocity, is about 3 milliseconds. So you're going to get, out of those 3 milliseconds, you have to get about 16 levels of resolution. And your scanning frequency is going to be in the order of 10 kilohertz for the keyboard in order for it to be anything sensible. And that's your round trip frequency. Because it's multiplex, because you're driving 10 columns, you're actually every time you're reading switches at a rate of about 100 kilohertz. So you're interrupting the processor every 10 microseconds to go, I need more switch data. Any jitter on that, your keyboard feels crap. If you're trying to do something else, well, good luck, right? Even modern chips have like 2 milliseconds interrupt overhead, so that's 20% of your capacity of your chip absolutely banjaxed. And for 50p, you can solve this. So please, people, make decent bloody key mix. I have people who became successful musicians and composers and arrangers asking me why every single keyboard every single keyboard they try and buy, even from companies like Nord, who know what they're doing, synthesizer keyboards just feel rubbish. And he said, look, there are 3 keyboards I get on with. There are 2 axioms and there's a Novation impulse. And I said, right. The thing you need to know is that Paul Whittington was a product manager in all 3 of those. So musicians care, and people notice. So there's my first bit of preaching. Hallelujah. Other thing I had to do was change the way the analog path worked. Main reason for that is this. October 2020 was a very bad month for audio. On the 22nd, Chris Huggett died, and on the 20th, the AKM factory burned down. And AKM was quite unusual in that they had their own fabrication plant, and they did all their R&D all under one roof in Japan, and it all went. And probably everybody in this room knows this, because it was in the midst of a semiconductor crisis. So stocks were very low anyway. All of a sudden, all new chips just disappeared forever. 18 months later, they managed to rebuild the factory, and they started making chips again. But after 18 months not in the market, everybody who was their customer had to respec and start using other manufacturers' chips. And so they're basically high-end now. And all of these cheap things no longer exist, so it's not a number of pounds. I couldn't even get a price for this. So he had to redesign that stuff. But the advantage of it was it's quite cheap. He knew what he was doing. And the other thing he did, which is quite sneaky, is dual rate stuff. So you've got really strange sampling rates because they're derived from a 48 megahertz clock. But the oscillators are run at 93 kilohertz, and the reason for that is the top octave becomes less critical. You can ignore what goes on in the top octave. If it aliases, it doesn't matter. If you don't generate those harmonics at 40 kilohertz, it doesn't matter. And it means that your approach to wavetables can be a bit more relaxed. So that's clever and a bit sneaky, but of course you're doing twice as much work. And the effects stuff ran at half that speed. What I did was I took a bit of a risk, and I ended up splurging a whole load of money on a completely separate chip that does everything. And it runs at 64 kilohertz because that's a nice kind of compromise between the 2 rates. It has a DSP in there, but no SRAM, so you can't run chorus or reverb. And basically it becomes a bit of a mix matrix. It's incredibly expensive because it's made by analog devices, and that's what they do. But the advantage you get from that is the fact that because it's a rather modern codec, it's basically got its own input stage built in. It's everything at the front end runs at a ludicrously high speed, so you don't need any op amps on the input, so you save a bit of money on that. We saved a bit of money on the VCAs at the output because it's doing its own mixing and matricing, and it has even straightforward DSP, and it is quite useful to have. And there's a few other things that we could simplify, so we saved a bit of money. So redesigned control board, go down to 2 layers because it's cheaper that way. It's quite a big piece of PCB. Nothing else that's particularly interesting about that. Went from physical switches to membrane ones, of course. And it's got a processor on it, the microcontroller there. Everything else is pretty much the same as what Chris did. He had a whole load of shift register to do switches and LEDs, and a whole load of analog multiplexers. Very boring stuff, right? The kind of thing that if you were doing a control surface, you could sort of fart out without thinking in a couple of weeks. So it's all very straightforward. The main board looks very similar to Chris's again, except it's got a nice 2-position big power switch on the back. And a few components we changed for expediency reasons because we were using them in Malevolent already, the first product. The only thing I'm ashamed about at this board that I couldn't do anything about is that if people are production engineers, you'll notice that I've had to use 2 of the same size and same type of connector on the board. I didn't get a choice, right? Joystick board had already been designed, it was 10-way. Keyboard we bought in, it was already 10-way. And of course, if you're in a hurry at a trade show and you're desperately trying to put these things together and take them apart and upgrade them, at some point you misplug them. Nothing blows up, fortunately, they just don't work. But don't do that in production. That's a bad thing to do. Naughty Ben. If I could do something about it, I would. But anyway, we've added a key scanner, got a nice big codec there. We managed to get a couple of the quad VCA chips off the board and saved ourselves another couple of dollars. Everything else is fairly ordinary. Taking apart the firmware. Now, the firmware is mostly oscillators and effects, right? Chris Huggett did the thing with the shape control, so you have an oscillator originating in a shape where you can mess around with things, and it was clearly a work in progress that he hadn't finished, right? It's a wavetable lookup. Everything is a wavetable in his original design. So sawtooths and squares, they're all MIP-mapped wavetables. And then the shape control just does a delay, another lookup, and an add. So it gives you a bit of phasing. If you put a square wave in, you get this kind of weird pulse train out. If you put a sine wave in, you still get a sine wave out. Good design practice suggests that the shape control should always do something interesting. So I ended up just rewriting all of the oscillators. That architecture is still used for sawtooth and nothing else. So if I press init patch, we had a nice sawtooth and you change shape. You get a bit of delay and add. And of course, because you're delayed by half a phase, it goes up an octave but sounds the same timbrally. So it's a comb filter. If you go to square, far more classic PWM. So when he did it, you don't get even harmonics, now you do. Sine wave is interesting because how do you make a sine wave interesting? So we added some FM synthesis to it. And when you turn the knob one way, the carrier frequency is the same as the audio frequency, so you get odd and even harmonics. Other way, you get only odd harmonics. And that tends to be used quite subtly. You know, if you want to do a mellotron, then you have these things just slightly off center, and you get some nice little effects. You have to, don't you? So it's quite nice for those things. It's just slightly off sine. What else do we have here? Triangles. Triangles are boring, but you need to put them on synth. Just really for. But you know, we messed it up by just having a sort of bouncing clip, so you get a little touch of aggression. And then the organ effect is something that Chris actually had in his synth. And when I was taking it apart, I found him putting together harmonic tables where you have fundamental frequency 2 times, 4 times, 8 times, 16 times, all the way up to, well, it'll be 1,024 times, but octave harmonics. And he's clearly putting together a shepherd tone, so in its natural habitat, this thing sounds like this. But of course, if you go up an octave, the only change to the waveform timbre is you lose a fundamental frequency. Everything else is the same, and if you're a bit crafty with high-pass filters, you end up with never-ending scales. And I think that was kind of his intention to put something like that in. I made it a bit more useful because the delay and add didn't make it particularly useful, so if you turn the knob one way, you get some odd harmonics you can play with and the shepherd tone illusion breaks apart. And the other way, you lose a fundamental and you get some other harmonics, and it's a little bit like the kind of thing that somebody would have if they were comping along on a Hammond organ. And so it's just a bit more playable. And the wavetables, you know, you want the aggressive Roland JP style wavetables to give you lots of harmonics you can mess up. So completely changed the way that part of the engine works. There's now only one bit of wavetable looking up, and the ramifications of that is that the amount of time I spend in the oscillator changes quite dramatically. The hungriest ones are weirdly wavetables because you go into Flash and you do a whole load of reading and interpolation, and that stuff is quite slow. You can't move it all into RAM because if you're modulating the shape, you don't know which 2 tables you're going to be using. So that takes, each oscillator takes 130 microseconds of my 2 millisecond budget to run. You'll see that Blit does what you expect. It gets more demanding as you increase the fundamental frequency. My lookup tables give up above about 7 kilohertz, and you just default to a sine because they're MIP-mapped, they get shorter as you go up, and it just ends up sounding horrible if you don't give up at some point around that. You end up with aliasing and all kinds of other stuff because there's only so much an interpolation algorithm is going to do, just trying to save memory. And Blit, as you would expect, the demand goes up with increasing frequency because you've got more wave transitions and you're having to deal with those. But actually it's quite effective. And if you put all this into a spreadsheet and do a bit of maths, you kind of get to about 3.6 voices now. Because he was driving a current control surface, Chris managed to get 2 voices out of this synth before it was basically beginning to fall apart. The reason for 4 oscillators is you have your 2 main ones, a sub. You also have oscillator 2 is really 2 oscillators. And there's a detune effect, so you can change the frequency between them in the mix of them and just get a bit more fatness. So there's 4 oscillators per voice. So you make a you make a button to give you chord polyphony, because that's a very nice thing to have, and musicians like to be able to play 4 notes at once. So we can do that, and as you can see, I stuck labels over the original buttons because we thought we could do quad mode, and there is a bit of a compromise because 3.6 is not 4, and so when you find yourself, I mean, we could have spent an extra £2 on the chip and got ourselves something faster, but we were committed by now. So what happens is, if you're playing something that's got all the oscillators running and all the effects running, and it's quite fat, and you play a 4th voice, the detune oscillator drops out and you can just hear it. Okay, now when I stop playing the top note, the envelope will recover, and when it's back down to 3 oscillators, the detune will come back in again. So it's a bit of a compromise, and we'd rather have 4 voices and have to do that occasionally. I mean, if you're playing 4 notes and you've got chorus on and you've got reverb on, it's already going to be fairly fat. So people aren't going to feel particularly disadvantaged when you take one of the oscillators away from them. That was a compromise. And otherwise, funneling 4 voices into 2 analog signal paths has some interesting ramifications for what you do with your filter settings, and the fact that you've got 1 analog VCA, and so you kind of fake it in envelopes by using a digital gain, and then everything gets wrapped up in the analog so that the analog stuff takes effect. So that was all quite fun. We got there. Of course, all of this stuff does rather complicate the loop, and this is some code I inherited from Chris. He likes tabs, I like spaces. But you can see he's looping every voice, looping every sample. You get one output per loop. W0, OSCset is his wavetable. So first dimension is the wavetable number. Second dimension is what octave you're on, because as you go up higher, you generate fewer harmonics. And the third one is where you are in that wavetable. So first 3 lines, he's generating oscillator 1. He's shifting it and generating a shifted version of the oscillator 1 for the shape control. Third line is the sub oscillator, so 0, 0 is a sine wave. Then the next set of lines where he's generating W1, oscillator 2, W2, oscillator 2, detuned. It's all very clear. You can see what he's doing once you look at the code for a bit. Some saturating clipping at the end, and he's just noise being read a sample at a time. Random number generator is a bit slow on this, which is why it takes 75 microseconds to fill a buffer, but it's not so slow you can't use it. And the trouble with putting all these checks and measures in and changing the way things are and making the oscillator more complicated, of course, is this sends up about 3 times the length. You're running all of these checks. You've got little things in, so when you turn the oscillator off, you still need to spin the phasors. Otherwise, if you bring it back in again, phase relationship has changed with the other notes that you're still playing, and it's timbrally different. And so all those little things you have to watch out for. And if you're really interested how this works, just freeze frame it afterwards. I want to talk about the reverb, because this was really interesting. This is something I would not have come up with on my own. Here's reverb, right? And you have your low-pass comb filters where you delay and you add. Low-bass comb filters in this case, because I just got this diagram from the internet, and for some reason they thought that was what it was. And then you have these serial passes at the end that are quite similar architecturally. But the idea is that you add these delays and you add these filters, and everything sort of feeds back into each other and it fattens things up. It's a complete illusion. This does not have that in. We don't really have the processing power to make that work. And so if I turn level and time up, we've got 1 comb filter, we've got 2 all passes. And the way we stop it sounding horrendously metallic, as anybody who has designed a reverb algorithm will know it does, is by frequency modulating the delay. And so you'll hear it going quite pitchy. I mean, you can have a 30-second reverb time. Who offers you that? But you can hear the pitch wandering a bit. So it's really just an effect, and it's just if you turn it down to a sensible level and play. Not that sound. We'll go for an init patch just so you can hear it. It's a comfort reverb, right? You're not going to be using it for... But it's still quite interesting and springy, and it doesn't sound awful. That was something that Chris kind of went and did on his own, and I tweaked the coefficients a bit, but that's quite interesting. auto-generating code. At some point, here's another bit of best practice. At some point, you're going to want to auto-generate, if you're writing in C, as I am, the program stuff. When you define a pattern where everything sits in memory, you have maximum and minimum values for that parameter to be. You have MIDI messages pertaining to that parameter, so when you tweak it, you want to send MIDI out. When you get MIDI in again, you want to decode it and know what parameter that goes to. You have flags, so you know when that parameter changes, which part of the control surface do you update, which part of the synth engine do you recompute. All of this stuff is data you need to manage. Now, C++, you will do it through creating a class that has those parameters in and you'd access those classes. You don't do that in C. You make some code that auto-generates. And Chris would use a C preprocessor for this, and don't do that. And the reason why you don't do that is firstly because the code ends up quite inscrutable. And you have these defs and these undefs, and unless you make it generate those interim preprocessor files, you can't see what it's doing to your data. And the other thing that's bad about it is it's a C preprocessor, right? It's not a scripting language. You can't make a reverse lookup table. When you get MIDI data coming back in, you can't, if you want to decode what parameter that pertains to, you have to generate all that stuff in runtime when you turn the synth on. And so really what you're trying to generate is a whole load of static tables like this, where you have minimum, maximum values. When you press the init button, you want your initial settings. You want a nice big enumeration so that when you're setting different parameters in your code, you actually understand when you go back to it what you were trying to do. And you want some MIDI decoding tables, and you want the update flags and things like that. Do yourself a favor and use a proper language. I know somebody who did, when I designed the mini Nova with Chris Huggett, I did it in Excel, and I used a piece of C just to change the Excel back into something like that. But don't use a write-only language. Don't use Excel, because every time you want to change a formula, you have to mess around with it. Don't use a preprocessor, because it's just too limited and too inscrutable. And then, there's all sorts of, it's a gift that keeps on giving, so that's the correct way of doing it. And of course, you might need a linear to logarithmic transform in order to make your volume control work. And then you can just define some line segments in Python, and it spits out code for you that's ready to use. You don't have to do anything in a text editor. So, just write these tools. You can do them in a couple of hours, and you'll thank yourself. And this should be obvious, but this is the fourth synthesizer I've collaborated on, and it never seems to be obvious to my colleagues. And if you go and look at GitHub repositories, it's not obvious to them either. But it's part of code planning. And everything, coming down to code design is really a demonstration for your framework. You're not writing a synth, you're writing a set of reusable tools, so you can make synths and controllers over and over again. And you end up with a library like this, as I did at Novation, where you have a piece of switch debouncing code that does things like auto-repeat and hold detection that you can use in everything you make afterwards. And you have, what else do we have? Potentiometer code you don't use anymore, but it's all gone into analog_controls.c. But things that do like slip rings and detents for pots, all of this stuff that you use, again, keyboard scanning. Keyboard scanning is really hard to get right because there are so many edge cases, and once you get it right, wrap it up, use it again. So this whole sort of load of reusable modules that any traveler should have, and that means that your code's already had a few hundred hours of test coverage when you come to use it again. Again, more obvious to C++ people than to C people, it seems. Where next? I didn't set my clock, so I have no idea how long I've got left. Somebody would be quite so kind as to... Brilliant, I've actually paced it well. Okay, so I worked for this with PWM, and Chris Huggett's no longer around. And the question is, what happens after this? It was Paul's intention basically to make an analog product, then a hybrid product, and then a digital product. And he's got like the first row of his matrix, and then you kind of iterate through those, and you become a competent synth-producing company. The world deals us funny hands, and he's got a good team of people working on a digital synth at the moment, but actually from a marketing point of view, there has to be a very good reason why that isn't just a plugin. If you're not doing anything interesting to the signal in an analog domain, you're basically writing a plugin with a hardware control. And so we're thinking about what we should do, because the worst thing you can do in the world is put out the wrong product. You're just throwing money away. So where do we go next with this legacy of things that we got from Chris? Well, one interesting thing is because we now have a good relationship with his estate, and of course he gets royalties. They get royalties from every sale of this. One thing we were able to do was keep talking to them about what Chris had on the back burner and up in the loft. And so there are things we can do in future. Our competitors kind of dictate the direction we go in, because in some ways they block off pathways, in other ways they're setting the expectations that our customers are going to have. Our customers are going to ask for things and sequels, which they already have, and reviewers have as well. There are things that look good on paper. You know, it's a multi-dimensional problem, what you do next as a product from a commercial point of view. And always when you make something of this complexity, there are things you wish you did and you would go back and do differently. There's no delay effect on this, for example, and there really should be. And one of the things we found, in while we were talking to Chris's widow, is she went up into the loft and brought this down. And if anything gets screen grabbed from this talk and gets put on dozens of YouTube videos, it'll be this, because this was at one point going to be the British answer to the Fairlight. And they had this demoed at a few trade shows back in the 80s, and a few grainy black and white photographs that had been photocopied from Sound on Sound back in 1984 and faxed to people multiple times exist of this. But as far as I know, this is the first color photograph of this and the first new picture to be taken of it in about 40 years. But it was a polyphonic OSCar with a whole load of other wave sampling and re-editing facilities, and it was supposed to be something about as capable as a Fairlight, a big workstation. And people are interested in this, but it never saw the light of day. I think OSC ran out of money, or they didn't quite have the capacity or wherewithal or determination to finish this project. So that's something. We probably won't do anything with that. I mean, what do you do with that now that the market's moved on? You recreated it in all of its glory today, nobody would know what it was for. And if Chris was going to reuse aspects of it, he would have done in the intervening 40 years, right? The good parts of that will end up in Supernova or Ultranova or any other synthesizers he's produced since. It's just an interesting curiosity, and it's good to have a good relationship with his estate. At the other end of the market, you have people setting expectations against your will and permission. So in August, Behringer put out this picture, and there they are with an OSCar synthesizer, although it's not right. And you can feel the misery wafting off this picture, can't you? They've taken something that was a kind of classic and rather expensive and valuable synth, and they've divided the knob count by 3, and they've put their own controls on. I mean, it's hard not to see mini keys as an insult for something of that complexity, isn't it? And you know they're going to put it out for about £3.50, so it's not going to have true analog paths in there, right? They're going to frig it in the digital domain. It's going to sound shit, and it's going to cheapen the brand. And people are going to go, "We love you, Behringer, and we're not going to pay more than £20 for anything ever again." And I hope that doesn't happen, right? We don't want them doing this, and we've asked them not to, but you don't make too much of a fuss because it ups the ante. So, you know, if you do Behringer, go on Make Our Day. But I don't know what so you have these things as well that constrain your expectations. And in the middle, of course, you have bona fide people making really, really nice stuff. So this came out at the same time as Mantis, and it does a bit more, right? It's got 5-voice polyphony, hence 5. And you can play this outside. It's made by Sequential, which is now part of Focus, right? And it does a bit more than our synth does. It's a bit more controllable, but it's a very different kind of value proposition, right? Same sort of retail price. And Paul was explaining the difference, the perceived difference in the market to me by saying, well, when he went to the NAMM show with this finished in its kind of version 1 incarnation, people were saying, "Have you seen the Sequential synth?" And they were also saying, "Have you heard the Mantis?" Right? So this is about control, and it's about timbre, and it's about having that interesting filter architecture and all the rather eccentric features. And it's about the sound palette you can create from it. And so you end up, there's got to be a reason why you're playing, and you find that, and you work out what your strength is, and you play to it. And so if we do something else based on this, you know, be interesting to do it in the OSCar territory with the permission and blessing of of Chris's estate. So we'll see where we go with that. And that is my last slide. I've rounded it off, so here we go. Thank you very much.